Let's use these blocks as a visual to do a coding challenge together. We can start with a brute force solution, but then we're going to figure out how to optimize our code to run faster. So I got 5 blocks laid out here, and what I want to do is find out all the 2-number combinations that add up to a target number, which is going to be a blue block. So to solve this the most brute force way, what I can do is take every single block and compare it with every single other block and see if it equals the target that I'm looking for, and just collect all those combinations as my solution. So I have a white block that I'm going to use to loop through the array. And so every time a white block touches something, that means that I'm on that number. That's my iterator. So here you can think of 1 through 5 as an array, and we're just looping through. And as we loop through, we're comparing 1 to 2 to see if it equals 9. No, it doesn't. We're comparing 1 to 3, see if it equals 9. No, it doesn't. 1 to 4, see if it equals 9. It doesn't. And 1 to 5 does not equal 9. And then we're going to take our white block and iterate to the next number in the array, which is 2. We're going to compare 2 to 1. No, it does not equal 9. We're going to compare 2 to 3. No, it does not equal 9. So we're basically taking every block and comparing it to every single other block to see if we have something that equals our target blue number. So we got done with the 2s there. Now we're going to move on to the 3s, and we're going to just keep going forward because we really don't have to go backwards. Like, we know we already checked the combinations back before. So that's a small optimization right there that we can make. And then we're going to compare. We can go back. We don't have to go back, but we can. And we check 4 to 5, and we see that 4 to 5 does equal 9, and that does give us a solution. So I'm not even going to check the 5s. It's the last one. We know it's been checked. The answer is obviously 4 and 5 for a simple array like this and a simple target like this. But the problem is when this algorithm has to scale. When 1 through 5, you say, is 1 through 1,000,000, then the number 1 would have to be checked with 1,000,000 values. Number 2 would have to be checked with almost 1,000,000 values. Number 3 would basically 1,000,000 values. So when this scales, you have to check every single number with the rest of the numbers in the array, which can be a lot, especially for the starting numbers. So in big O notation, how we measure time complexity, this is considered big O of n squared or quadratic time, which is not very optimal solution. So let's see how we could find a better solution. Like, what can we do to optimize this? And what that is trading space for time. So let's loop through this again, but this time we're going to look at the numbers and take a complement of each one when we compare. So we're going to look at 1 and we're going to say 9 minus 1 equals 8. We're going to store 8 inside of what we're calling the data structure, or a hash map. Hash maps have keys and values assigned to those keys. So here we're saying 8 is the key and the value is the index of that 1, which is 0 in this case. So now we can keep going, move the white block, iterate through our array, go to number 2. But now we want to check if 2 is a complement already in our hash map. If it is, then we know, since we subtracted previous numbers to make a complement, we know if that complement exists in the hash map, that those 2 numbers added together will equal to the target, the number that the complement is assigned to as far as index. Check if 2 is equal to something in our hash map, which right now is only 8. And it's not equal to anything, so we know we can just move on. We don't have a complement, we don't have a match, we don't have a solution. So now we can calculate the complement for 2 against 9. That gives us 7. Put that in there, and then we just move on to 3. And now we need to check if 3 is in the hash map as 8 or 7. And so this is really fast because hash maps are keyed, and to check if a key is in the hash map is a big O of 1 or constant operation. Is a very quick operation. We don't have to loop the hash map or anything like that. And that's why hash maps are so powerful in order to trade space to save time. So we see 3 is not in the hash map, so we can calculate its complement as 6 and then move on. Check if 4 is in the hash map. It's not in there. Calculate its complement, which will give us 5. And then we know then we can move on to 5, and we do find 5 in the hash map. And since that 5 in that hash map has a value that's assigned to an index of another item in the array, in this case it's index 3 with the item 4, we know that the complement of 4 is 5, the complement of 5 is 4 when you're trying to make 9, and we know that that's our solution, and we can return with that solution, or at least one of our solutions. So why is this solution optimal? Well, you might notice that we only loop through our main array one time here. We don't check one number, then loop through the rest of the array, check the next number and loop through the rest of the array, check the next number and loop through the rest of the array. Like, we just looping through one time, and we're using this data structure in order to help save us time. But that does trade for space. So we're adding extra data here. You see I've added more blocks, which is extra data that I have to store. So this solution is actually linear, and it scales with the size of our input. So if I have one array 1 through 5, it's 1 through 5. If I have 1 through a million, it's 1 through a million. So it's big O of n linear time. So now that we're using space, we can also measure the space complexity, which is big O of n linear time, because in worst case, we're going to have to store a complement for every single number. And if we call n the length of our array, then it will be big O of n. So since this array is sorted, there's actually one more thing you can do to optimize this without using extra space. Let me know if you know what that is. So I hope this makes sense, how you can optimize this from the brute force solution. Let me know if you have any questions, and thanks for watching the video.